Okay. Okay. I guess maybe it's time to call the meeting to order. It's 6:05, so thank you for your patience, and mostly thank you so much for coming. My name is Richard Epley. My wife is Carol in the back, and she and I were sitting at the falls 10 years ago, almost to the day, and wondered why it was so hard to see the falls. And so we thought, well, perhaps we could talk to Central Hudson and get them to tear some trees down, and, which they did. And one thing led to another, and the Conservancy was born out of that interest to just do something good for the community if we could. And that then has developed into a cadre of the most amazing group of volunteers that you can imagine. And I know some of them are among you here, so kudos to you who have helped along the way to get this all done. Over the past 10 years, I guess one of the most things that we're happiest about is getting a little tract of land down by the creek, which was a DOT right-of-way, getting that land transferred to the town of Marbletown so it could be used as a walkway and a little trail that people could use to go along and see the creek and see the amazing geological formations that are visible from that little walk. We were there one night, and one afternoon I guess it was, and along came a gentleman and his wife. They were obviously very interested in looking at the geological formation, anticlinal fold that you can see over there. And we got into a little discussion, quickly to find out and discover that this gentleman, whose name is Bill Heins, was a very eminent geological scientist and has a very rich and very wide background of assisting in exploration of every kind of geological formation, every kind of geological situation that exists. And he now is on the forefront of helping our large oil companies and others involved in that industry to transition into the green energy realm, which we all know is very much to be desired. So Bill has been one of these amazing Renaissance men who was able to do marvelous things in a very changing world. So I don't want to take much more time from your enjoyment of his remarks, but only would like to say that if you enjoy this evening, which I know you will, we want to invite you to come back the next 3 Thursdays in July and learn more about our country and about our region and about these rocks. So with that, Mr. Bill Heins, who does never like to be referred to as a doctor, but if you've picked up our book, you will see that his doctorate is from University of California at Los Angeles. So, Bill, it's all yours.
Thank you, Richard. Let's see if we can get the projector fired back up.
Take a little bit.
I think it might be warm.
Quite well. While we're waiting for it to warm up, if there are 10 people in the audience who would like to participate briefly, you'll notice that there are 10 little bits of blue tape around the perimeter of the room. Because I have to leave a little bit of material for the other 3 lectures in the series, we're only going to cover all of geological history tonight and play tectonics. So, and in the part about geologic time, I would need some people who can stand on the blue dots, because that's going to represent different events in the history of the Earth that are going to play a role later in the series. So the first one is up here, if anybody's really bold, and then there's 2 more. Okay, then there's 3 more back along this side. Carol's on one, he's on another. And then there's 2 more in the corner, and there's 2 more up here.
How long? 2 hours?
No. Just a few minutes. Okay, we've got.
Projecting, I don't. Yeah, turn the light.
Where is the?
Turn those off.
So as Richard has set up this series, there's going to be 4 lectures, and all of them are about right here where we're sitting. We want to. That's one of the things that I really enjoy about being an earth scientist, is that I can do my science anywhere, because it's the study of the earth, and wherever you are, that's where it is. And so we're going to turn our attention specifically to the rocks that are here in High Falls and exposed at the falls. But those, like any kind of history, the particular moment in time or the particular incident that we're interested in always has a context. It's always there for a reason. And, hey, okay. Just had to undo the...
There's just a piece of plastic there.
Bill went out.
There we go. All right. So as I said, tonight's topic is geologic history, geologic time, and plate tectonics. Because in the subsequent lectures, we'll turn our attention specifically to the rocks that are exposed here at the falls. But we want to know, where did they come from? How did they get all bent out of shape the way they are? And what's happened to them from those formative events until the present day? And in order to understand that history of the rocks right here, we want to put it in the context of all of Earth's history. And so that's the first part of the talk, is to look at geologic time in its entirety. The next thing is the rocks that are here are the result of many processes that take place in the Earth. And plate tectonics is the underlying force that drives all of those processes. So we want to take a little glimpse inside the guts of the Earth and understand why it moves the way it does. And if we get that out of the way for tonight, I think we'll have earned our cookies. So let's start with the history of the Earth in about 10 minutes. So we're going to use as the metaphor for all of Earth's history the football field at Slippery Rock State College. And that this really is the football field there. And we're going to start out with the beginning of the Earth literally from stardust, 4,580 million years ago. And at that time, it was just a chaotic cloud of miasmic dust floating through the cosmos, starting to coalesce because of the gravitational attraction of all the little dust particles. And it took about 70 million years for them to get well enough organized that we had distinct planetary bodies. And we know, because we went there, we know that the moon was already fully formed, and there are rocks that are 4,510 million years old, or 4.5 billion. So we know things were organized by then. And if you look at the down marker marching along the football field, if we started out at the 0-yard line, it took up till the 2-yard line to get all that together. So then, the first evidence that we have for the Earth. We know that the Earth was here, we know that things were happening, but all of the events were so traumatic and so disastrous for the rocks that were there in the past that they have lost all memory. And it's not until rocks of 4.28 billion years that the Earth finally starts telling us something about what happened back in the day. And these old rocks are in Hudson Bay, Canada. And you see that we're now up to about the 3-yard line. So the Earth remembers pretty much back to the beginning of its history. However, the evidence is very sparse. The next really big thing that happened that's important for us personally is the accumulation of oxygen in the environment. And that's thanks to microorganisms called cyanobacteria. The cyanobacteria were around for a long time, for that whole most of the 50 yards up to where we see them. But we know that they really took off right about the midpoint of Earth's history because we have these things called banded iron formations, or BIFs, that are at this age, 2.33 billion years old. And what happened is the cyanobacteria finally got their act together. They started making more and more oxygen, and as fast as they could pump it out, it was captured by rusting iron. Because iron had been perfectly happy for half of Earth's history, it didn't have anything to oxidize it. And finally, when the oxygen came, all the iron rusted, and when it finished rusting, then there was nothing more to grab up the oxygen, and it could start accumulating in the atmosphere. And that was a great thing for multicellular life, and ultimately for guys like us. And life stayed pretty much unicellular, or very simple, for most of the rest of the history. But suddenly, really abruptly, at 538.8 million years ago, there was this incredible diversification of life. All kinds of weird experiments in how to organize multicellular life, many of which didn't quite make it. But these are all fossils that come from the Burgess Shale in Canada. But this was a sudden explosion in life. And you see that we're down to the 12-yard line now, so we're getting really close to the present day. So now it's time to step inside the room. And this Cambrian explosion is our good dear colleague here at the front of the room at the first blue dot. So that represents the Cambrian explosion. And now all the rest of geologic time that remains is around the perimeter of the room. And that's kind of so remember, we're at the starting at the 12-yard line, and this is a little bit more than 36 feet, but it's kind of the right scale. And we want to place the events that we'll discuss in the rest of the lecture series now in this last little bit of history. So the next thing are the first rocks that we see in this neighborhood. And where's Bill? He's got his Friends of the Shwangung t-shirt on. We know that this is popular local stuff.
The other Bill's over here.
There you are. So these are, in the local context, the oldest rocks. You see them coming into town. There's some chunks over at the falls that are serving as barricades. They're really tough, tenacious, gritty rocks, and so they make great millstones. But that's a kind of a hallmark of this area, and the deposition of that unit started 427 million years ago, which is right here. Now, there was many different kinds of rocks that were deposited on top of the Shwangung conglomerate, but the youngest of them that's really exposed in this local area is the Glen Eyrie limestone, and it finished depositing at about 407 million years, where the gentleman with the blue shirt is standing. So you know that all the geological history as far as making the rocks happened in that little time window right there.
Since you're at me now, since this is connected with science, shouldn't we be measuring things in meters?
We can. I grew up in the oil industry, so I have to be bilingual. That's all right. And if you want to see this particular outcrop, that was the best picture I could find on the internet. There is a little outcrop. It's all overgrown, and I couldn't find a very good picture right by the police station at Marbletown. So if you go up there and you come up the road, drive from High Falls up to Marbletown, on your right-hand side where it says speed zone ahead, there's a little cliff there. That's the youngest of the rock formations that we'll talk about, and that's this part of time. All right. Now, you may notice that there's no rock around here that's lying down. Rocks, when they start out their life, are flat on their back. They're just horizontal. And if you see a rock tipped up, it means that something drastic happened to it. And in the second part of today's talk, we'll discuss how that can happen. But at about 393 million years ago, back in the corner here, we had a big train wreck of a tectonic event where a big island called Avalonia slammed into the side of North America, and it created a mountain range that is about as big as the mountains that we see today in Papua New Guinea, where the island of Irian Jaya, Papua New Guinea, is having the same kind of train wreck with Australia. And it's pushed up huge 16,000 foot mountains, and the same thing happened right here, back in the corner. Now that process, let's keep going forward, that process of continents drifting and accumulating reached its apex just about 300 million years ago at the end of the Pennsylvanian period, beginning of the Permian, when all of the continents on the Earth were accumulated together in Pangaea, which is back, where Carol is. So at all that you can see, you can see Hudson's Bay there, I think, pretty well displayed in North America. Africa is snuggled right up against the east coast of North America. South America is down to the south. And you see that there is that enormous snow-capped mountain range there. And that was off to our east back in 200 or 300 million years ago. Now, like other things, nothing lasts forever, and the continents keep drifting and they pull apart. And we can see this process of continental rifting going on today in Africa. So there's a few dots there on the left-hand picture of the globe. You can see that there are some lakes, and we zoom in the middle picture to show you a little bit closer view. This is literally the eastern part of Africa is being ripped away from the rest of Africa. Ultimately, it's gonna float off, and there will be a new ocean in that spot. And exactly that same process happened, because you notice we don't have the huge mountains here anymore, and we don't have the huge continental landmass. Europe and Africa, which were next to us, are long gone. Well, that process started at about 232 million years ago. And the way that we know that it was happening is because, just like these rift lakes in Africa, the process gets started and it never quite knows where it's going to be successful. And some of the tears don't quite make it all the way. And one of those tears in our neighborhood is the Newark, it's called the Newark Rift. And we know that there were lakes just like these lakes, shallow lakes in East Africa, because we can find some dinosaur footprints down in Blauvelt, New York, that mark that time, 232 million years ago, when the continent was starting to pull apart. We had shallow, muddy lakes, and we had dinosaurs running around in them. All right, now we're up to the Catskills. Around 200 million years ago, and we'll discuss how this process works in the second part of the talk. But associated with pulling the continent apart, there can be mild uplift of the edges, and what's going to be the Catskills when we get to the present day started to go up 200 million years ago. However, these rocks that we see on the skyline today, they weren't anywhere near the surface. They still had a mile or more of rocks over their head, and so that spot, that's the top of the Catskills today, was still deeply buried. But at 200 million years, which should be there, it was started on the way up. Now that rifting process, the separation of the different land masses, really got going by about 180 million years ago, to the point where we had an honest-to-goodness ocean in between North America and Africa, and there was real oceanic crust being formed. And we'll talk about how that happens in the second part of the talk. But at 180, where are we now? I think, no? Yeah, there you go. At 180, we're at the opening ocean. And then jump way forward to 15 million years up here near the front. And today's Catskills, the actual rocks that we see at the surface today, are just about up to the top. And then at 1.8 million years ago, which is just up at the very last dot, so I counted around 100 tiles around the perimeter of the room. And that 1.8 million years ago, when ice ages started globally, out of the last 1 foot tile, it's only the last few inches is the 1.8 million years. And if we look at the picture of the Hudson Valley in the ice age 13,000 years ago, that's about like the hair on your head, that last little fraction at the end of the time. So the point of this first part of the talk was just to give you a sense for how long geologic time is and where the events that we'll discuss over the course of this month fit in the picture. But why? Why does it do that stuff? Why do the continents move? Why do the mountains go up? Why do the oceans go down? Why? Well, we'll tell you. It's all about plate tectonics. So, to understand plate tectonics, we have to dive into the guts of the Earth. And, oh, that's an egg. Anyway, if you just keep that model, that mental model in your brain, the inside of the Earth is a lot like a hard-boiled egg. There's 3 important parts to the Earth, just like there's 3 parts of the egg. The egg's got a shell, it's got a white, and it's got a yolk. And the Earth is, now this is a true scale. This representation is everything in its proper proportion. There are 3 different parts of the Earth too. The outside part is called the crust. And it, on average, here on the continents where we live, it's about 35 kilometers thick. See, I'm talking metric now. 35 kilometers, it's about 20 miles thick. And at the scale of this diagram, that line is the right thickness to be 35 kilometers thick. If you're using the model of the eggshell is a little bit thicker, proportionally speaking, than the real crust of the Earth. And you'll notice that I want to prove to you that I'm a real scientist. I gotta earn my PhD there. I show you because I wrote a Greek letter. That Greek, you thought I was talking about the Philadelphia Phillies. No, but that's the Greek letter rho, which we use to describe density. And you notice that there's no units on there. This is a relative term. It's a specific gravity. And this is, the rocks of the crust are about 2.7 to 2.9 times more dense than water. So, and you could pick the units you like. You could use grams per cubic centimeter. You can use tons per cubic meter. It's all the same. 2.7 to 2.9. The thing that we want to keep our eye on is the relationship among the different numbers I'm going to show you. And we won't go in deep into mineralogy, but the crust of the Earth is mostly made out of silicate minerals. So they're made out of silicon, oxygen, aluminum, and some other light stuff. So they are relatively light minerals that have a low density. And that's why the crust is because it is literally floating on top of all the rest of it, because it is the least dense stuff. So then we hop down to the next part of the Earth, which is the mantle, which in our egg model would be equivalent to the white of the egg. And there's 2 parts. There's a solid part that's absolutely rigid, and it acts like the crust. Mechanically, it's like the crust. So sometimes we call this outer light green part of the upper mantle, along with the crust, we call that the lithosphere. But then underneath it, there's a squishy bit. Now, if you could hold a piece in your hand, you would still think it was a pretty solid rock. But it can deform over the millions and billions of years that we were just talking about before. It can flow. And that part of that's the lower mantle. All of it has about the same chemical composition, and it is made out of different kind of silicates that include in their crystal structure iron and magnesium. And as a result, they're much denser than the rocks of the crust. Density is about 4.5 to 5.5. So the reason that the crust is on top of the mantle is because the crust is so much lighter. It's floating up on top of the mantle. And the mantle in the squishy part can actually flow. And then the inside of the Earth, equivalent to the yolk in the egg model, is the core. And it has a distinctly different composition. It's mostly iron, and it's really dense. So it's like 9.9 to 12.2, multiples of the other kinds of stuff. And there's a solid core and there's a liquid core. And again, the composition, the chemical composition is the same. It's just the physical state of the material is different. And the solid core is constantly growing. It's always getting bigger at the expense of the liquid core because the liquid core is freezing. The liquid core is freezing and making the solid bit in the middle. And that's going to be an important aspect of plate tectonics that we'll get to in just a moment. So I chose the color scheme in this model, the greens and the reds, and actually the crust is blue, to highlight the difference in temperature between the interior of the Earth and the exterior of the Earth. That molten iron in the core is really hot, 5,200 degrees Celsius. And at those temperatures, Celsius, Fahrenheit doesn't really make a difference. It's really big. It's a really big number. In fact, the very inside of the Earth is almost the same temperature as the very surface of the sun. Now, that sounds pretty dramatic, but if you realize that the very surface of the sun is way cooler than the rest of the sun, then we can kind of, fudge that comparison. But it's true. So we've got a really hot interior of the Earth, and then we've got a cold exterior, 14 degrees C, that's 57 Fahrenheit. That's, if you took the average of every day of every spot on the Earth, all over the Earth, that's the temperature. But the main point is it's a big difference. Between the inside and the outside, there's a big thermal gradient. Now, where does all that heat come from? First thing is, you remember the coalescing from stardust at the very beginning? Like all those little particles that were spread out over over thousands of light years, they all slammed into each other to make the solid planets. And that gravitational attraction and collisions made a lot of heat. So they turned, kinetic energy of their motion into heat, and it's still left over from way back then. In addition, there is that latent heat of crystallization. So if you put a tray of water into your freezer at your house, it turns the liquid water into ice. And in the process of turning the liquid water into ice, it's got to take a lot of heat out of the liquid and throws it out into your room. Well, the same thing is happening in the interior of the Earth. As the liquid iron freezes to make the core, a lot of heat leaves the liquid. And that's part of what makes it so hot down there. And then the last bit is radioactive decay. One of the elements that I didn't talk about in all of the minerals in the mantle and the crust is potassium. We need potassium in our diet. My doctor keeps telling me, eat more bananas, don't get those leg cramps. But potassium actually some of it is radioactive. And that decay, there's enough potassium in the rocks of the mantle and the crust that as it decays radioactively, it makes a lot of heat. So those are the three sources of heat that make the inside hot. Now, what happens when you got something that's hot on the bottom and cold on the top? Well, you can do this experiment yourself. Put a pan of water on the stove, and the stuff at the bottom, as it gets hot, it expands. It grows a little bit, and so it becomes less dense. And as it becomes less dense, it wants to rise. When it gets to the top, it cools off, it shrinks up a little bit, and it sinks. And you then have a circulation called convection. And this phenomenon happens not only on the pan on your stovetop, or you could hard boil your egg if you really wanted to. But it happens inside the Earth too. That the same phenomenon of heating up, getting less dense, and rising goes on in the mantle too. So the mantle is picking up heat from the core, it's getting less dense, and it's rising, because at geologic timescales, it can flow. And so we have a rolling boil. Just like a rolling boil, you can have a rolling boil in your saucepan, we have a rolling boil going in the mantle of the Earth. And where two upwelling parts of the convection cell come together up at the surface of the Earth, that's where we have a tension. Those upwelling arms of the convection cell grab the crust and pull it apart. That's what makes the ocean go there. So you can see here in this view of the globe that Northwest Africa fits very nicely up against the east coast of North America. And if we were to look farther down south, you see that the easternmost point of Brazil would snuggle very nicely into that corner of Africa by Nigeria. So the Atlantic Ocean is a relatively new phenomenon, as we pointed out before. It started up in our neighborhood, started opening up 180 million years ago, and it's opening up exactly because of these divergent convection cells in the mantle that are pulling the surface of the Earth apart. And a little bit of that melted mantle leaks out right at the crack in the middle, and that's what creates the oceanic crust. That's why it keeps growing apart, because that material from the mantle keeps feeding the little break. Now, does that suggest a problem to anybody? If we got the Earth spreading apart at one place, and the continents are moving apart from each other, anybody would,
on the other side.
yes, you would have a collision. So the Earth isn't getting any bigger. Unfortunately, we could probably use a little more real estate. The Earth is not getting any bigger. So in order to accommodate this spreading there at the mid-ocean ridge, we got to consume crust somewhere else. And you'll notice that that's in the diagram, that's this thing called the trench. So when oceanic crust, it's created at the mid-ocean ridges, but it's also consumed at trenches along the edge of the continent. So now we need to look a little bit more closely at the crust. In the previous diagram, we had it true scale. The crust was so thin we could only draw it with the really skinny line. But we want to zoom in a little bit and realize that there are a couple of different flavors of crust. There is continental crust, that's what we're standing on right now, and there is oceanic crust. That's the new stuff that's created by at the mid-ocean ridges as the oceans are forming. Now the continental crust is thick. It's tens of kilometers thick, many, many miles thick. And if you had to describe one word, it's kind of like granite. So there's sediment on top. I mean, there's just dirt that we're standing on. But underneath, somewhere under our feet, there is really solid crystalline tombstone kind of rock, which is like granite. And that's what the continental crust is. We can compare that to the oceanic crust, which is created at those mid-ocean ridges, and it's very thin. It's only a few kilometers thick, and it is like the rock basalt. We don't have any around here, unfortunately, but it's a black rock like you would find in Iceland, for example, or on the Columbia Plateau in Washington State. And it is more dense than the continental crust. Now both of them, this 2.6 and the 2.9, both of those are way less dense than the mantle. So both continental crust and oceanic crust float, but they don't float equally well. And now, if you think about it a minute, you will realize why the oceans are oceans. That there's a big hole, or there's a low spot on the Earth's surface where the oceanic crust is, because it's more dense than the continental crust, so it floats lower in the mantle than the crust does. I mean, if you think about throwing a sheet of plywood and a big log into the Hudson, the sheet of plywood is really dense. It's hardly, I mean, it's really solid. It's hardly less dense than the water. So it's going to ride real low on the water surface. The log, on the other hand, has got a lot of holes in it, a lot of airspace. It's going to float up high. Same thing with the continents and the oceanic crust. And if we were to look back at we'll go forward. There we go. No, I'm going backward, sorry. Okay. So we'll see that the ocean is not uniformly deep. Some parts are shallower, some parts are deeper, and that has to do with the relative density of the oceanic crust. When oceanic crust is created at the mid-ocean ridge, let's see, and I jumped ahead of myself. When I say younger is hotter, so when you create the oceanic crust at the mid-ocean ridge, it's just come out of the mantle. This is freshly crystallized liquid mantle juice. It's really hot, it's very buoyant, and it floats up high on the mantle. That's why the mid-ocean ridges are ridges. They're like mountain chains in the middle of the ocean because that basalt is really buoyant. It's hot and buoyant. And as it spreads away from the ridge and it cools off and it gets older, it gets denser, and so it sinks down. And that's why you find the deepest ocean where there is the oldest crust. Okay, and then when the oceanic crust bumps up into the edge of a continent, the oceanic crust always loses. The continental crust always rides over the top because it is much thicker, it is much lighter, it's more buoyant, and so when the two of them collide, oceanic crust always goes down, and it makes this characteristic trench as we see, for example, off the coast of Peru. When continents collide, then that's a different story. That's a big train wreck. So if you have a big, thick, light, buoyant piece of continental crust on one side and another big, buoyant piece, and they slam into each other, nobody's going to go down. And so we see where India collided with Asia, for example. If you look in the ocean, you can still see the skid marks where India was trying to put on the brakes, but it just didn't happen, and it slammed right into Asia and it pushed up the Himalaya mountains. And the reason I bring that up here is because we had the same kind of car crash right here in our neighborhood 420 million years ago, and that's why all the rocks around here look like a rumpled up carpet. And we'll talk about that in some subsequent iterations of the lecture series. All right, so that's what I wanted to talk about, and I wanted to leave you with the thought that everybody can rock geology. And all the people on this picture they have several things in common, but two most important are they have a PhD and they have a job. These are all people that I've worked with in my career, and it's just to point out that unfortunately I am kind of the prototypical demographic of a geologist. I'm an old white guy with a beard. But you don't have to be that in order to be a geologist. You don't even have to be able to walk. Carol Fall, the lady in the wheelchair in the black and white photo, she was one of the best paleontologists of the United States, and I had the good fortune to learn paleontology from her. All the ladies across the top I worked with at ExxonMobil. Chucha and Kim, for example. Don't ever let anybody tell you that math is not for girls. I'm a real geologist. When the numbers get beyond 10, I got to take my boots off. But those guys know math really well. And yeah, you can be in a wheelchair, you can have no legs. The reason Laura is you only see like the tattoos is because no legs. But you know, none of that gets in the way of using your brain to understand what's going on with the Earth. And so I hope that over the course of this lecture series, we'll all together have the opportunity to figure out what happened by using our eyes and using our brains and taking the evidence of the processes that run the Earth and see how they're responsible for the landscape around us. So I hope that we'll have the chance to do that in the next installments of the lecture series. Yeah, next time, July 14th, same bat time, same bat station. And we're going to talk about when these rocks were young. And if I have time, I hope I didn't look, we do still have some time. I would really like to entertain questions and talk to y'all, because that's always the most fun part of any of this business.